Lab 4 Oscillations by Paige Mayfield. So an introduction to this lab is we used a mass located on a fixed spring and then it is stretched then released, using Tracker to plot the positions data from the point in which the spring is released. We used GrowScript to create a computational model to predict the motion of the object, and we compare the predicted motion to the observed motion. We plot the energy changes, and we have some assumptions for this lab, but the mass of the object is equal to 0.402 kilograms, that the fixed end of the spring is located at the origin, and the only energies included are kinetic, spring potential, and gravitational potential energy. So these are the fundamental physics principles that were used. We used gravitational force with the assumption that gravity is equal to 9.8 meters per second squared. We used spring force. We used gravitational potential energy. We used spring potential energy. We used the equation for kinetic energy. And then we did the energy principle. And we did the velocity update formula and the position update formula. So the initial conditions of our experiment are the mass is equal to 0.402 kilograms. This is the initial position of the object. This is the initial velocity. T is equal to 1.524 seconds, and T is also equal to this. K is equal to 6.83, and Ks is equal to 6.83. L is equal to 0.123 meters. So here's our experimental data, and the origin of attachment is at 0, 0. The axes are assumed that plus x is right and plus y is up. Our starting frame is at 5, and our end frame is at 104. And we made sure to set the orientation and calibration points for this. So here's the computational model. We set the initial conditions, and we calculated the components of the spring, which includes L, L hat, and S. And we can calculate initial energy. Here, we set T is equal to less than 9.307. We calculated the forces. We did the positions, velocity, spring force, and time updates. Here we calculated the energy changes during the while loop. And here we plotted the energies for each time step. We plotted the time versus position, Y, for the predicted motion, and we import observed data and plot. And the plot allows us to observe the position values, which allows us to compare. Here are the comparison of the graphs. On the left, you can see that the observed is in red and the predicted is in blue, representing a very similar slope and graph. And here on the right, we have UG equal to red, US equal to green, kinetic energy equal to blue, and E equal to orange. And here we can compare the X and the Y estimates to resemble a very similar graph and T values. Here's the analysis. Is the energy principle satisfied? Yes, it's a closed system. Delta E is equal to 0. The energy is conserved throughout the entire experiment. Regardless of the types of energy, increasing and decreasing, the total energy will always be 0. The total energy will remain 0 because there is no transfer of energy to the surroundings due to everything being a part of the system. The oscillation periods were computed by the X and Y position status are similar, which makes sense fundamentally because the calculations for the period relies on the mass of the object and the spring constant. The difference was likely due to inaccuracies when plotting positions in Tracker. In conclusion, the computational model was a fairly accurate prediction of the motion of the object. The change in energy is always equal to 0, and there are small discrepancies in the positions graph, which are likely due to errors when tracking or calculating the spring constant or L naught. In an alternate experiment, I would improve the accuracy of the model by being more precise when manually tracking positions in Tracker. Thank you.